recording.
Saying you love it is okay.
Ah, dear. Welcome to the 21st century.
It's good to be back.
Yes.
Good to be back.
So is this a clip of actual bacterium, or is it Cheetos in space? What is
I think
this?
it's Cheetos that were scanned and then animated,
There you go. Okay,
possibly. I don't know.
awesome.
If you're eating
real one.
Cheetos that color, oh my goodness, you're gonna need help.
In the
I have
color of
no
Cheetos?
idea how
I mean-
desperate college students are in dorm life anymore, do you? Have you forgotten?
I was not a college student, ever was. I am newly single and I don't have my 4 children every other weekend. So I have learned to eat like a college student.
Oh, there you go.
It's great. I love it.
Yeah.
My 4 children every other weekend.
The old joke, when it wasn't a joke really, was beware the black jello and the gray pudding. Sadly, that wasn't
Black
a joke.
Jello?
Black jello.
I think that would
Yes.
sell, actually, you know.
Yeah, and it sounds like
That
it should
black
be
water, you know, there.
some fun Halloween treat, but it wasn't. Our food service company got fired in my sophomore year because the illness rate on campus was just too high. And they said, it's not us, but when they fired them, it got better.
That's
So,
crazy.
yeah. We also, one year, small town, the local source of water was in Eureka Lake, town of Eureka, Illinois. Small college, 500 students, a little less. So the water supply was the lake. We had really horrible winter that year. We had a long string of sub minus 10 Fahrenheit weather. The lake froze all the way to the bottom, which meant we had no water for a while. And then as the lake melts, it melts from the top down. You think about this. And then the ice pulls up, right, from the bottom. And when it does, it pulls up megatons of silt and rot and dead fish because the lake froze all the way down. And the water was unusable for 2 months. And so we had to wait until the town had to wait till it got warm enough, and then they could get somebody to basically rebuild the water filtration system. And so it was milk and canned juice for a long time. Yay, small
was it?
town life.
Where was this small town?
Eureka, Illinois. I went to Eureka College, which has 3 important graduates. President Ronald Reagan was a student there. Nobel laureate Stephen K. Binkley, biochemistry, was a graduate there. And then there's me, the 3rd really important person. The worldview according to me. But no, I had a Nobel laureate for my chem teacher, and I had a president of the United States as my commencement speaker in a college with 450 students. So it's kind of awesome.
So it's nice to see all the greetings back. You know, we were gone for a week, but we're back, and we're real happy about it. So that's awesome. Pekka says,
Everyone misses us. It's nice.
Pekka says, glad you're back, Scott. 1 week was enough without ES broadcasts. It really disrupted my daily routines. Almost had to watch teletext or TT News.
Oh, goodness.
Wow. I'm
That's
glad
a fate
we
worse
got back
than
in
death, right?
time. Let's see. Billy Beckett, I have a question for Dr. Barth.
Yes.
Had the Mars-size impactor not happen and the moon was not created, what would Earth's mass be? Ooh.
The current planet Mars is about, I'll wait till after the end.
Okay. All right, we got a little feature here. Featurette. You're going to like this one.
In 1871, Charles Darwin speculated in a letter to a friend that a warm little pond might be life's birthplace. A warm soup of chemicals bathed by energy from the sun would have been, well, comfortable for molecules to come together in new ways and create life.
Darwin was way, way ahead of his time. A nice little warm soup is going to get you a long way.
Jeff Bada of the Scripps Institution of Oceanography in San Diego has spent his career working to understand the early Earth soup of chemicals. He began under the direction of perhaps the most famous scientist in origin of life research, Stanley Miller.
There are in the history of science turning points where we suddenly see the history of Earth and life differently. In the early 1950s, Stanley Miller, the eager graduate student, and Harold Urey, the Nobel Prize-winning mentor at the University of Chicago, conducted this astonishing experiment where they made an early Earth environment.
It looks like this sort of a Frankenstein-type apparatus, but actually it's a very carefully thought-out design.
Bada sets up a modern-day test of the 1950s experiment on Miller's original lab equipment.
One flask contains water. That's to simulate the ocean. The other flask has just got the gases in it. So this is the atmosphere.
Just as it does in nature, water from the ocean evaporates and rises into the atmosphere, where it condenses and returns to the ocean. Miller simulated what he believed to be the atmosphere of early Earth, with different gases, like ammonia and methane. Then he added a spark of genius.
Miller and Urey decided to use a spark to simulate lightning because that's such a ubiquitous process in the atmosphere of the Earth.
That was the real inspiration, these little electric sparks. They acted like simulated lightning.
The energy from the spark of lightning breaks down the gas and water molecules, so they can undergo further chemical reactions.
To their astonishment, when they turned this apparatus on, after only a couple of days, you started seeing this pink color developing. And then a few more days, black, oily goo is forming around the electrodes.
The electrodes get covered with new substances, organic compounds usually associated with life.
And it wasn't just any organic compound. It was amino acids that make proteins the ingredients for life.
Amino acids are the building blocks of life. They form proteins, which are the key component of muscles and other tissues.
People thought, aha, this is a key step in the origin of life.
And you really believe that you can bring life to the dead? That body is not dead. It has never lived. I created it.
The experiment raised the fear that a Frankenstein creation, like in this classic film, was just around the corner.
It's moving.
People were saying they made Frankenstein in a test tube.
It's alive! It's alive! Now I know what it feels like to be God.
Had Miller and Urey cooked up life in a test tube?
Many of the news headlines were saying life created in the laboratory, life created in a test tube. Well, of course, that was wrong. The real news was that he'd made these compounds that are part of life.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance, and really pleased to be back with you after being gone for a whole week. I was so excited in getting the show put together. And of course, today is, how do you know, number 21? Is that right?
21.
21. Okay. So, and this is the origin of life. And as I read through, I hope you downloaded Dr. Barth's study guide, because I was getting more and more excited as I was learning more about some of the hypotheses and the idea of a condensation of maybe our atmosphere, of the environment itself creating life, and the other part. And I'll let Dr. Barth elaborate on this, but it's how life, once it takes hold, how really resilient it is. So which is very is nice to know in a day and age when we think that we're destroying our planet. So. Which is, not very accurate, but anyhow, we have a lot of catching up to do. Annie's with us, as you can see, and Annie, what do we have planned for this week?
Well, we have quite a few things planned for this week. Our normal schedule, so that's really good. It's nice to be back. We all miss Scott a lot, and so I think we didn't know what to do with ourselves.
Oh, really?
The employees and our viewers. I think we were a little.
I had hidden cameras. I saw like a major party going on here. So
maybe. I don't know.
Maybe.
Okay, so I'm going to share our screen so we can go over the calendar. Okay, so always go to Explore Alliance and then hover over to Explore Alliance Live.
There we go.
And you're going to scroll down to the bottom. Well, not all the way to the bottom, because then you'll miss all the wonderful things that are happening. So our normal schedule, of course, today, how do you know? Tomorrow's going to be the Open Go-To Community with Jerry Hubble. It's a great show. I would recommend watching it. He is very informative. He's really good at what he does. It looks like he's going to be talking about star type measurements and other measurements. Of course, then we have our 58th Global Star Party that evening, which is amazing. Then, of course, on Wednesday, it's me, then Kent with First Light Chronicles. Then we have, we're changing our schedule a little bit this week. Dan George is going to be on for On the Wing, and then we'll have Cameron Gillis do Camstronomy. That is an amazing show. It's been a great opportunity to watch him document the sky with the cell phone. It's so cool. I think I highly recommend watching it. And then we're going to go then that evening we have Caitlin Ahrens with 7 Months of Science. This is a show that we do once a month with her. She is, I'm going to click on it. You're going to see who she is. Dr. Caitlin Ahrens, and she is from NASA. And it's just a great opportunity to be able to listen and learn from her. So watch it. It's only once a month. So our Wednesdays are really packed right now. And then starting Thursday, the 19th, we're going to have Astronomical League Conference. We will not have shows Thursday and Friday because we are hosting this show. We'll be streaming it live. And so this is their affiliate page with us. And then if you go here and click, this is for their event, their 3-day event. And you can, I think you can still register.
Yes, you can. And there's like $8,000 in door prizes. It's probably more at this point because they were receiving door prizes, which I thought was totally cool, from their constituent astronomy clubs.
Yeah.
Normally, they would reach out just to manufacturers, but they went out to the clubs themselves, and they opened up the toy chest here. So there's
I mean,
lots and lots of prizes to win.
Yeah, I mean, look, I'm scrolling down now through them. That is a lot. There's a lot of stuff on there that you could have the opportunity to win. So it's all virtual. All you got to do is register. It's free. I would definitely be a part of that. I was going to see what their schedule was. And then they're gonna have David Levy on there. Chuck Allen's going to present awards. You know, they have some Richard Gott, Ryan Claremont, you know, so David Eicher, Alan Dyer, and John Goss. It's going to be a great event. So highly recommend you guys watch that. It's 3 days. So we will not be having our regular Thursdays and Fridays show because of that, because we're going to be streaming that for everybody. And then, the rest of the month is pretty much the same schedule until we get, I thought I saw in September, I feel like there was something in September that we were going to be doing. I've got some more things to add, but without Scott here, I get lost sometimes. So even though I take a million notes, but I also have customer service I have to take care of. So,
Yes, you do.
So,
yes, you do.
so and poor Tyler is laid up, and so I've been trying to help out as much as I can. So, but yeah,
You've done a great job. Thank you so
thank
much,
you.
Annie.
But yeah, there's a lot going on. So just keep following. If you look on there on that calendar, I try to update it and fix it and add things. And if something's missing, if somebody sees that something's missing and they're just curious about it, please email me. Please email me. And don't forget, we also have, we'll be announcing the astrophotography winners. And then for the Galaxies contest this week sometime. And then the PMC8 survey, will announce those winners as well. So,
Okay,
yep. So
cool. So
Did
lots
we
of
have
incentive.
do we have
Go
a
ahead.
winner to announce from last week's giveaway on my show?
I unfortunately do not have that.
Because we had okay. Well, there's your,
We'll have to,
No,
we'll have to send out
there's your
something.
homework from teacher. No, we had a giveaway on program 20.
Yep.
And we had
Yes.
a question. And,
Yes, and I have all the answers to the questions. I
Good.
actually do. That they're in my email, and
okay.
I'm just gonna be honest. I dropped the ball.
No, it's okay. Okay.
So yeah, there we go.
It's not
I got
about
out
being
of
perfect, it's
routine.
about
Yep.
being
Didn't get
better
out of
every day.
routine. I didn't have
Got out
Scott.
of routine. It can happen to us all.
Yep, so, all right. Y'all have fun.
All right.
Thanks.
Thanks, Annie.
Bye.
Nice to see you
Bye.
again, Annie.
Nice to see you.
Yeah. So Daniel, I just wanted to tell you that, I kind of started off the presentation talking about how excited I am about this subject, but, the origin of life is a really compelling subject matter, and,
Very much
you know,
so.
and how psychologically, how we think about life in general, there's certainly, I'm just so you guys know, I'm a vegetarian. I avoid doing things like killing insects and stuff like that. So, because, you swat at a fly, it's going to fly away. It doesn't want to get hit, these kinds of things. So the idea of survival of living things is ingrained, into almost everything that lives. And in fact, I think it's in everything that lives. But going through the, your dissertation in your guide, it made me really wake up to the idea that, this planet, beyond what's on this skin of the surface of the planet and our lives and our communities and what we do and stuff like that. We kind of think that life just kind of revolves around human beings. All right. And what really sunk home for me is that, there's, I'm not sure where, each individual sides on, commentary about the idea that humans are destroying the planet. Okay. But we may be destroying something, but really
Not the planet.
who we're destroying is us. Right. And we're not the only life that's here. Right. And so, there was stuff here long before, and I assume long after.
Long
us
after.
as well. So,
Yeah.
so anyway, it's just good to be alive. That's what I think.
Two essential facts. The first is that never in the history of life has the planet been so changed by anything that life did not rebound and flourish. If you destroy 95% of the species with a giant meteor impact, well, guess what? You've just opened up huge numbers of ecological niches, and there's all these energy sources which are not being used, and life will diversify into the new niches. The second fact, and this is the reason we must go to Mars, and Robert Zubrin is right, Buzz Aldrin is right, hell, Elon Musk is right. We must go to Mars because every species ever born here has died and gone extinct here. Every single one. You look at a geological timeline of species and you see, here's a point where the first reptile, the first fish, the first bird, and you can take any species. Here was where they appear in the fossil record, and here's where we shot the last passenger pigeon. There is a day when the last member of the species is alone and is no longer able to find a mate to reproduce and fill its destiny. And it expires. Every species created here, born here, depending on your point of view, every species has died here. To be a multi-planet species is the only way to be safe. And the environment, we have this almost, it's hubris. Oh, we're the ones changing the planet as if it's all been peaceful and nice until we got here. That's ridiculous, Scott. The environment is routinely upset.
Yeah, we have poisonous atmospheres. We had every
two theories.
Worst thing that you can think of has happened to this place, right?
Two theories were competing in Darwin's day. One was called gradualism. The idea that, oh yes, things will go along tomorrow pretty much as they were today, and things change only very, very slowly over time. And Darwin, with his theory of evolution, said, yes, there's changes and there's slow changes over time. The other theory was called punctuated equilibrium, which says one day you're a happy dinosaur, and the next day, what's that streak of light? And everybody dies. It's the idea of an earthquake. You're living in a seaside village, you're fine. One day, this big tsunami comes in and wipes almost everybody out. Punctuated equilibrium says, yeah, things go along, and they're almost the same, almost the same, almost the same. And then there's this traumatic change, and everything changes. Well, when we go back, when we circle this back around to life on Mars, and I get asked a lot, well, when I talk about Mars, do you believe there's life on Mars? And the first thing I have to say is, wrong question. Unless you're talking a philosophical idea here, science isn't about belief, it's about data. It's not about polls, it's not about popularity, it's not about opinion, it's not about politics, it's about data. 20,000 scientists agree that, you know what, Galileo's day, 99.9% of the scientists agreed that the Earth was in the center of the solar system and it was fixed and not moving. This was the view of everybody in government, everybody in religion, everybody in politics, everybody in business, and darn near everybody in astronomy and mathematics. They were all wrong. You know what? On the other hand, there's two other true things. when you say, guess what? I have an idea. Y'all have been wrong forever, and I'm here to lead you to the truth. You're either really, really smart or you're a crackpot. And the ratio on that is very extreme. The number of crackpot people, every once in a while, I get books in the mail, Scott. My New
Yeah.
Theory of Gravity by Bob the Crank. And I've got about a dozen of these on my shelf. People said, I have a new theory of gravity. You should be teaching this in your physics and astronomy classes. I'm like, okay, let me take a look at this. So Newton's wrong, Einstein's wrong. And you're like, okay. We all know that John Dobson, wonderful man that he was a profound supporter of the steady state theory. He didn't give any credence to Big Bang. I'm pretty certain John was wrong about that. It's okay. Nobody's right about everything. Percival Lowell gets hectored a century after he died. He gets hectored because, he was wrong. There weren't linear features on Mars. He was a great scientist. He was a profound and dedicated astronomer. He discovered amazing things. But on this one thing, which he was very public about, he was wrong. Okay. And then we come to the life on Earth, and do you believe, or life on Mars? Do you believe in life on Mars? And it's the kind of question that either takes a one-syllable answer or an extended dialogue like we're having today. The one-syllable answer is yes, I believe there is life, microbial life on the surface of Mars. I believe it's in the interior. I philosophically, for many reasons, believe this is true. If you talk to me as a scientist, as a biologist, as an astronomer, I'm going to tell you there's not enough data to decide the question. And we're going to get into some of that. My personal beliefs mean nothing. You know, Dobson's belief did not change the fate of the Big Bang Theory. Copernicus's belief in the Earth as a planet, heliocentric theory, did not change the reality of the world. So do I believe it? Yes. I'll just put it out there. Yes, I do. And scientifically, I say, but I can't prove it. People say, well, if you can't prove it, then why do you believe it? And that's what we're going to talk about today. And this week, next week, we're going to talk about why I believe it. And I'm going to lay out my case, and I'm going to let people decide for themselves. But we're going to go back, and we're going to talk about life on Earth first. There is a wonderful quote that I will give you from an old professor of mine, Mr. Grimm. He refused to be called Dr. Professor. He wouldn't take it. He wouldn't answer you. Mr. Grimm used to say, the greatest miracle in creation is that the whole damn thing is self-assembly. If you think about it, do you want a galaxy? Do you want a black hole? Do you want a star? Do you want a planetary system? You need enough primordial hydrogen, helium, lithium, and time. If you have a big enough cloud of primordial gas, stars will self-assemble out of this material. Gravitation, dust is produced, solar systems are produced, stars ignite, and people say, and here we get to the the creationist atheist view of reality. I don't believe there's any conflict between science and religion. None, zero. It's promoted by a lot of people who have something to gain or sell. But frankly, if you're a scientist and you're a person of faith, what you're studying is how God pulled it off. What are the methods of the divine providence? Einstein said, I want to know God's thoughts. The rest are details. Okay. And if you believe there is no God, then what you're studying is, how is nature self-assembling? How does nature pull it off? Philosophically, I think you'd have a hard time separating out those two views. And I don't think there's any conflict. There's the who, there's the how. Same three letters, different questions. Religious people want to know who. Science people want to know how. I think it's two sides of the same coin, but there's another thing I'll throw out there for everybody to shoot at. But when we talk about life on Earth, one of the things that we find, the whole universe self-assembles. And I think you'd find very few people who would disagree that if you have enough hydrogen and primordial materials, gravitationally it will collapse, you will form stars, stars will synthesize, new elements. Second generation stars will produce planets because there's now metals. By the way, folks, astronomers say metal is everything from helium on up. There's hydrogen and there's metals. Astrophysicists separate the periodic table real simply, element one and then everything else. But you get the larger elements and you can form dust particles, you can form solids, you can form planets by accretion. The whole thing is self-assembling. We call this autogenerous, right? And means it puts itself together. Well, you go back and again, in the video, you picked a great intro video, by the way.
Oh, great.
We go back to Russian biologist A.P. Oparin and Scottish biologist J.B.S. Haldane. And they said, you know, Earth's atmosphere is obviously not the original atmosphere. They take a look and say, gee, what kind of stuff belches out of volcanoes? Sulfur, methane, carbon dioxide, oxygen reacts with everything. If you killed off every plant today, there would be no oxygen in the Earth's atmosphere within a century. Oxygen is so reactive, it will be absorbed into the crust in a very short order of time, which is why we consider oxygen to be a life indicator. If there's an oxygen atmosphere, something has to be producing it. Otherwise, it wouldn't be there.
Mhm.
Much the same with the argument, methane is detected on Mars. Methane is much more often a biological product than a geological one. Does this or does this not indicate life? Yada, yada. There's evidence and data there. But Oparin and Haldane said the atmosphere of a primitive planet would be what we call, would not be an oxidizing atmosphere. It would be a reducing atmosphere. It would contain hydrogen, carbon dioxide, nitrogen, methane, ammonia, water vapor. And so you take a look at these gases and you realize what has transformed our atmosphere from a primitive reducing atmosphere to a modern oxygen atmosphere. And life did that. Life changed that. And Oparin and Haldane, they basically said, well, these gases are left over either from the solar nebula or from geological processes. And they hypothesized that UV light, they weren't very much thinking about gamma radiation at the time, but UV light and lightning would provide the activation and energy to break chemical bonds and allow them to reform and to cook our atmosphere into a rich brew of basically, they were thinking simple nitrogen compounds, carbon compounds. It was Harold Urey. He was the pioneer. The video mentions Stanley Miller. Stanley Miller was Urey's graduate student at the time. And Urey set up this experiment that we saw. Here's a flask, and into it, we cycle water vapor. And they tried it different ways, different recipes, right? But basically, ammonia, methane, carbon dioxide, nitrogen were the four ingredients. And they put in tungsten electrodes and they had bzz, 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 spark. And I think you saw one of those pictures, the guy's holding a Tesla coil. Looks like a brown cylinder with a metal pointer. Mm-hmm. So he's powering this high voltage, low amperage, basically like lightning strikes. And they did. They found out it didn't take long, about a week. And within a week, you start getting things like aldehydes, alcohols, carboxylic acids, amino acids, and this rich soup. And how did they decide what they had there, Scott? They were using spectroscopy, which has come into our story many times. We heard about how the early explorers, the early astronomers were trying to do spectroscopy. And of course, Lowell tried it. Others were more successful after him because spectroscopy requires that you shoot light through a gas and then you see what frequencies are absorbed by certain molecules. And by what's absorbed, you can decide what molecules are there. And of course, here on Earth, since they had a sample of the brown goo, they could do spectroscopic analysis. And, oh, here's a peak, that means methane. Oh, here's a peak, that means lysine, and here's different amino acids, and so they were looking at these, and they realized, gee, we have everything here except the self-replicating molecules. We have hydrophilic molecules, we have hydrophobic molecules, and those self-assemble into bilayer membranes that cells rely on. The only thing they didn't have was a self-replicating molecule. And generally speaking, what Urey and Miller found, and it's still true today, you need a longer period of time to get bigger molecules, right? You think about this. If you have a paint shaker and a bunch of Lego, right, in there, and you're waiting for Lego to self-assemble into bigger pieces, bigger clumps, guess what? You're going to have to wait longer, number one, for larger molecules to assemble, and two, you're going to have relatively milder conditions for big molecules to assemble, because big things are easier to break than small things, right? If you have a very large glass sculpture, it's very delicate and very vulnerable. On the other hand, you can see one of these lens balls, right? Or a small convex lens. You can drop them. They're hard to break. They're hard to chip. But large things are much easier to break. Large molecules are easy to break. So they were thinking about this primitive soup. The tide washes in. You get these tide pools. You get these materials. New water comes in occasionally. You've got salts. You've got minerals in addition to the basic atmosphere. But Urey and Miller said, you don't need the soup. This happens in the air. The atmosphere itself starts creating these complex molecules which rain out on the land, in the sea. Milder conditions now, right? The sea and puddles are not subject to the regular lightning strikes of the atmosphere. And so, gee, we refer to this self-assembly as autogenerous, and we talk about autobiogenerous processes. In other words, the question comes, is life self-assembling? Now, again, you get back to the atheist creationist point of view. Oh, well, life, God said, and then it was, or the person who says, no, let's not bring God into it. Then, of course, we've got the autobiogenerous. Life self-assembles. Well, if life is self-assembling, how long did it take throughout my lifetime? The date of the first evidence of life on Earth has continually been pushed back. At one point, when I was much younger, life appeared 1 billion years ago. The Earth is 4.5 billion. It's been pushed back to life appeared fairly shortly after the Theia impact that created the moon. That's impacting the Earth with a body the size of Mars. Someone asked the question, how much bigger would Earth have gotten? Mars is about 1/10 of Earth's mass. So Earth would have grown by Earth would have been about 85% of what it is now. A Mars impactor would inflate it to fully its current size. We didn't lose much. The moon is only 1% of the Earth's mass. So we talk about this and we look back and we say, oh, how old is the moon? Well, the moon is about 4.2 billion years old. Most of the Maria date from between 4.2 and 3.7 billion years ago. Life was on Earth when the Maria were being formed. Fossils, the most ancient fossils now date to about 3.6 billion years ago, which tells us that life appeared on Earth. You figured the Theia impact, an object the size of Mars hits you, the surface of the planet reliquefies. It becomes the lava hell planet, like in one of the Star Wars movies, right? They had the lava hell planet. Basically, the Earth would have been like that after the Theia impact. Well, guess what? Pretty much after enough time has gone by for the surface to re-solidify, life appears.
That part to me, I mean,
yeah.
If these major, planet surf destroying events have happened, and there's lots of evidence that it's happened a lot more than once. Okay.
Yes.
Right.
Yes.
That for to life to continue to respawn and diversify and clean up because you can imagine what the air was like and everything. It's just ultra polluted, hellish environment in every sense of the word, and yet stuff comes growing back. Not only plants but animal life and all kinds of life. So
what that says to me is that if we had a Mars-sized impactor again today, then essentially within a few 10, perhaps 100 million years, as soon as the planet re-solidified again, life would reemerge.
Yeah.
It would not be us. It would have a completely new evolutionary path, because evolution is a pachinko game. You can know what the averages are, but you never know what the individual path of a ball will be. So life would reemerge. Are we capable of destroying the planet? Not hardly, Mr. Hubris, not hardly. We are not. Are we the only species that's ever destroyed the planet? No, we're not. And we'll talk about that too.
Okay.
But Oparin and Haldane said, well, if you have this reducing atmosphere, the first life on Earth would have been anaerobic life. It would have been bacterial. It would have been anaerobic. That means, friends, that oxygen kills it. Why do you put hydrogen peroxide on a cut or a scrape? Because the oxygen that bubbles through the wound destroys anaerobic bacteria, which are things like streptococci and other really nasty infections. And so, hydrogen peroxide is a great disinfectant for anaerobic cells. These cells would have been in the sea, they would have been on the land. And at this point, the top of the food chain on Earth would have been bacteria. Perhaps would there have been some protozoans or some amoeboid life forms, that eating others? Probably. We don't know. We have no evidence of this. The earliest evidence is of colonial bacteria. In other words, bacteria like blue-green algae that grows in large mats and clumps. All right. So we see these mats, we see these bacterial mats and algal mats in places today. It's not unusual. And we have fossils of these things, and we can look in the fossil record and we can see these things. There was a great controversy, again, the Allen Hills meteorite, and they sliced it open and they looked in with a microscope, an electron microscope, and they said, oh, look, we see what appears to be a colonial bacteria type structure. Spheres strung along in a line, and oh, look, there's magnetite. So the only way we get magnetite today is bacteria oxidizing iron produces this kind of magnetite. And other people are saying, no, these cells are not the same size as Earth cells, so they obviously can't be cells because they're not like our cells. That doesn't strike me as terribly convincing. And the Allen Hills meteorite is one data point. Bink, it's 1 point on the chart. It's not if we found lots more of these meteorites and we slice them open and we're finding these sorts of fossilized nanobacteria sort of structures in all of them, then the challenge is, okay, if it's not life, then okay, Mr. Geochemist, Miss Geochemist, let's see you produce these darn things in the lab, because if it's not autobiogenesis, then it should be inorganic chem, right? And we should be able to produce the conditions. Nobody's been able to do that. Does that mean it's autobiogenesis? No, it means we're not clever enough to make something that looks like that in a geochemistry lab. Okay. Well, you get this anaerobic cells, and many of these cells are living by oxidizing. They are consuming, bioprocessing iron and sulfur. We find huge deposits of iron ore. How did that get there? We have good evidence today that what happens is large colonies of bacteria. There are iron ions dissolved in seawater. There would have been a lot more carbon dioxide. The seas would have been a lot more acidic. They could dissolve metals. And these bacteria are basically oxidizing the iron for the energy they can get out of it. And then they're using that to live, and they're depositing big beds of iron oxide, which is now iron ore. And you say, oh, is there that much energy in iron? Well, if you take aluminum and iron and mix them together and ignite them, you get thermite. Yes, there's a whole lot of energy in there. You ever seen a thermite reaction, Scott? Folks, look it up on the internet. Don't do it.
No, but it sounds like dynamite.
It's not. You take iron oxide, powdered aluminum, mix them together, and ignite the two of them with a strip of magnesium, and the aluminum pulls the oxygen out of the iron, generates enough heat that molten iron comes out of the bottom of your reaction vessel. Okay. You can cast iron things this way. I used to do that experiment in chem back in the 80s. They're not allowed to do that sort of thing now. But, there's plenty of energy. And we find life forms on the bottom of hydrothermal vents 3 miles below the surface of the sea. And what's coming out? Hydrogen cyanide, hydrogen dioxide, carbon dioxide. And what are these clams and these worms that live around the vent? They don't consume oxygen. There's no oxygen there. They're sulfur breathers. Essentially, they're metabolizing sulfur and iron.
Wow.
So we've got these earth forms. Well, of course, you never have an Eden without a snake, right? And so somewhere, perhaps about 4 billion years ago, there was an evolutionary leap, and some bacterial species developed photosynthesis, the ability to use solar radiation as an energy source. Well, you think about the life before photosynthesis. Their energy source had to be these biochemical soup that was in the seas and in the puddles and in the rivers, right? Their only food source was these atmospherically created organic molecules which were raining out. Once you get a species that can use sunlight, they don't need that anymore. They don't have to grow near water. They can grow anywhere because sunlight is now their energy source. And so, yay, photosynthesis. But what do photosynthetic cells all produce? We all learned this in middle school or elementary school. Plants produce oxygen for us to breathe, and we breathe out carbon dioxide, which feed the plants. But in the beginning, it wasn't like that. You had greedy little capitalist bacteria consuming sunlight, which other species couldn't, and belching out oxygen, which is a poison to anaerobic life. A deadly poison. What happens over a relatively short period of time is the atmosphere goes from basically reducing to oxidizing, goes from 0% oxygen, and we don't know how high it would have gotten. Probably considerably more than the 21% we have now, because we have lots of oxygen consumers in our environment. At that point, the entire environment was oxygen producers and anaerobic cells. And guess what? They poisoned the atmosphere in terms of what the first life forms were doing. The atmosphere was now poison. You would die on contact with the atmosphere. And Gilbert Levin calls it the oxygen holocaust. He said, oh, this would have been like a giant meteor strike. 95% of the species would have died. The anaerobic life forms, they're still with us. They are underground, deep in the ocean. Some of the anaerobic life forms, Scott, thrive 10 kilometers below the surface.
Wow.
They have not seen sunlight or free oxygen in billions of years. The oxygen holocaust did not sterilize the planet of anaerobes. You think about that. You have these shallow, top of the sea, top of the puddle, anywhere there's a little wet, dribbly spot. You have these anaerobic life forms living very happily. And now the only ones are the ones that could migrate underground. But the oxygen holocaust did not destroy them all.
Right.
We're going to destroy all the life on Earth. No, sorry, Mr. Hubris, it's not happening for you.
Right.
Does this mean we should just pollute the hell out of our environment? Well, don't be ridiculous. Of course we shouldn't. But, you know, so 90% of the living organisms, 95% of the species would have died of oxygen poisoning. So we get down and we have several points here. And we look back to the Copernican principle again. If you think you're special, you're deluded, right? Copernicus says, if your theory requires special conditions just for you, it's silly. You're missing the point.
Right.
So here's these points from this early story with Oparin and Haldane et al. First of all, no free energy source in the environment will remain untapped. For a few 100 million years, we had species which were being irradiated and nobody was taking advantage. Guess what? It's free energy. A species evolves and all of a sudden it's all for, you know, well, I can't eat that. More for me, right? If you ever go to a restaurant and somebody says, "Ooh, I can't eat onion rings," and you've got the big appetizer in front of you, you go, "Oh, more for me," right? It's a free energy source and you're not eating it. I'm going to consume more. So no energy source remains untapped. Carbon-based, mineral-based, radiative energy-based, doesn't matter. All sources will be tapped and life forms will adapt via evolution for this purpose. That's the first principle. Second, life tends, not absolutely, but tends to stabilize its environment. Life tends to form homeostatic relationships, symbiotic relationships, and it tends to stabilize its environment. That is not universally true. People who are worried about global warming will tell you, "Oh, we're tipping the Earth's atmosphere over." And I'm not sure about that one, but we won't even go into that today. But certainly take a look at our anaerobic and photosynthetic life forms. Well, something came along and completely polluted the planet, made it uninhabitable for the original life forms that were the master race, the top of the food chain, and they were driven underground and into the depths of the sea because these new life forms ruined everything. So life tends to stabilize in its environment. When the environment decays, it becomes hopelessly, lethally polluted. Life finds a way to utilize the poisons in the environment as a resource and thrive upon them.
And live on that.
We have bacteria, and we found this, didn't we? When the Deepwater Horizon well broke down in the Gulf of Mexico, and the catastrophizer people were saying, the Gulf will be polluted for a century. And the pollution was basically gone in 36 months. Why? Because there were bacteria that could live, and obviously had been living for a long time, on small seeps of oil and petrochemicals from the ocean floor. That's an energy source. It's going to be utilized. And guess what? Those organisms had a bloom. They had a field day. It was like the original photosynthetic life forms. And they're like, look, there's all this food. And yeah, all the terrible, terrible pollution went away. Why? Because something was there in an evolutionary niche, and all of a sudden conditions were very favorable, and it multiplied like nuts. So the third principle, life is almost impossible to extinguish via environmental degradation, via mechanical, physical, geological, or chemical means. When we have extreme hazardous conditions, we simply create an extreme evolutionary pressure, and we get extreme rates of adaptation. When the environment, it's kind of like when the going gets tough, the tough get going. when the environment becomes terrible for the existing species, evolution pushes to the extreme. What happened when we discovered DDT and started spraying everything? We got DDT resistant mosquitoes. Oh, DDT kills 98% of the mosquitoes. You know what? The other 2% are going to breed and they're going to kick your ass because they're like, DDT? I ain't afraid of no DDT. Why do doctors today hesitate? Why are they very cautious about prescribing antibiotics? Because we've all heard, oh, there's superbugs that don't die from common antibiotics. Tuberculosis makes a resurgence. Why? Because the strain that's coming back is the 1%er that didn't die from the existing antibiotic treatment regimen. So we see this again and again. We see it in medicine. And so you got to ask yourself, how hard is it to sterilize a planet? So we have 2 data points, Scott. One, life is an autogenerous process. Autobiogenesis occurs as soon as the planet is capable. Does it have the right ingredients? Is it in the habitable zone? Autobiogenesis occurs. And second, once autobiogenesis does occur, what kind of an awful disaster does it take to sterilize a planet? Okay. Consider the oxygen holocaust.
Well, a Mars-sized planet is not enough, right?
That's exactly right. Getting whacked with a Mars-sized planet was not sufficient.
A nearby supernova is not enough.
It's not sufficient.
You know,
if it's your star, you're probably in trouble. But basically,
probably when your star envelops your planet, at that point,
you're done.
Maybe that's
game over.
It. Right.
The corollary to life is almost impossible to extinguish is once a planet holds life, sterilizing that planet by anything short of a stellar catastrophe is virtually impossible.
Now, Daniel, you talked about a Mars-sized impactor hitting Earth and liquefying the surface.
Oh, the impact energy would have remelted the entire.
Right. Okay.
planet.
So, yet life comes back.
Yes.
I'm inferring that, or I infer that life is so deep in the Earth.
I don't think so. I think the process is so robust.
Okay.
I think the process is so robust. Can you imagine as an
But even in a liquefied environment?
Well, even if you say, oh, I'm sure it wasn't completely liquefied. We know what subduction is, right? Continental plates come together.
Sure.
And this is part of the convection in the mantle. Well, if you get hit by a Mars-sized planet, don't you increase the convection and therefore the subduction? Even if the whole planet doesn't remelt now, isn't the entire surface going to be rapidly recycled planet-wide for a period of millions of years?
Seems reasonable.
And if it gets hot enough to melt the rock, that's temperatures that's outside the regime of supporting life. If the rock is molten, nothing's growing on it. Lava is safe to eat because it's sterile. Don't try this at home. But, you get these ideas, well, wow, okay. And we see that within a few 100 million years, over the age of the Earth, this is an indistinguishable boom, boom event. The crust resolidifies and life appears. This says to me that this autobiogenesis process is so robust that as soon as the conditions are ripe, it happens. Now, you might say, oh, it takes 10 million years to occur. But in the life history of a planet, that's an eye blink.
Yeah.
So as soon as the conditions are right, and so the other thing we know now that we didn't know back in Urey's day, we didn't know this in Carl Sagan's day. Extremophiles. We've heard of extremophiles. We've found extremophiles adapt and thrive in almost any environment. We tapped into a subglacial lake in Antarctica that has not seen free atmospheric gas exchange or sunlight for 10, 20 million years, and there's an ecosystem there. It's very thin
Amazing.
because it's a zero-sum game. There's not a lot of free energy there, but life exists there. We go to the Atacama Desert. It gets 1 centimeter of rain a century. We find bacteria in the soil. We go to the Allen Hills dry valleys in Antarctica. It's underneath the freaking ozone hole. It gets the same amount of solar radiation as Mars. It's nuts. It's averages, 30 below zero year round? And it gets less than a centimeter of snow per year. And the only way you get liquid water is in the cracks of quartz crystals when a UV ray hits it and breaks down the ice crystal. And we find not just bacterial, but photosynthetic life. And we find what they call the biological crust on rocks. You take a rock, it has this crust, you scrape it off, you look, you warm it up, you give it some water, you give it some nutrients, and the bacteria start growing like crazy. They were always there. They're thriving to the extent that they're capable in the conditions they're given. These experiments where we've been finding bacteria 6, 8 kilometers below the earth. We're breaking into new cave systems where we know there has not been any human being there ever. And we're taking a sterile sample off the wall and we're finding biology deep in the crust of the earth. So basically, we see these extremophiles. And for 5 decades, 6, all of my life, what I've been hearing is life on Mars isn't possible because, and then we start the drum roll and the parade starts, right? The first float on the No Life on Mars parade is there's no water. And later on, they said, oh, well, there's not enough water. It's too cold. There's too much radiation on the surface. The soil is too salty. There's not enough free energy in the system. And every single time they come up with a reason why there can't be life on Mars, somebody else, a new rover, a new probe says, oh, look, there is water. There is enough heat. There are, oh, we found on Earth, things that live in mine tailings, in acidic, salty water. And oh, look, there's this scum of biological activity on this wastewater from mine tailings. Oh, look, you go find some volcano where sulfur dioxide, carbon dioxide are bubbling up through, and the whole lake is a hot, bubbling pool of acid. There was a documentary, somebody put on respirator gear and tried to row out in an aluminum boat. The acid was eating through the boat. They had to retreat. And yet, right at the very edge where it transitions, there's life around, there's bacteria and algae around the pond. Is there right in the middle? No, but you don't get universally horrible conditions unless you have a Theia impact. There's always this transition zone. Oh, there's hydrothermal beds at the bottom of the sea, and the water coming out is 230 degrees Celsius, and it would boil if it wasn't 7 miles deep. And the temperatures are horrific, and it's full of acids. And and there's this whole community of clams and worms and sea stars and everything living around it. None of them are oxygen-dependent respirators. They're all sulfur-dependent respirators. They're having a completely different biological metabolic process. And they thrive. Do they thrive right in the middle of the hydrothermic vent where the water is 230 Celsius? No, but 6 inches away where it's just a little cooler, boom, there's Mr. Clam, Mr. Worm, Mr. Crab, Mr. Sea Star. They're all there. And so you get this idea of extremophiles. Okay, well, let's take a look at the dry Mars hypothesis. If we take a look at dry Mars, Percival Lowell, oh, canals, dying planet, H.G. Wells, Orson Welles. basically the community said, no, 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 we're not going to go with this science fiction wackiness, and we're going to ostracize, these people. And for a long time, after War of the Worlds, 1930, if you were a scientist and said, I want to study the possibility of life on Mars, you weren't getting any research money, you weren't getting a position, you weren't getting hired. You're a crank, go away. We finally found, the early stuff showed Mars' atmosphere is very low pressure, very thin, very little atmosphere on Mars. Spectroscopic studies, such as they were, they couldn't detect water vapor. And when they did detect water, it's at the error limit. Oh, this detector is plus or minus 2%, and we're detecting 1.5% water vapor. So it could just as easily be a zero result. The early photographs, Mariner, was the first, Mariner 4 was the first probe. The Russians sent 9 probes. From 1960 to 69, they sent 9 probes. They all failed. Getting to Mars is hard. Even today, the failure rate for spacecraft going to Mars has, up until recently, never been better than 50%. It's a hard place to go to. But you get all this pressure to reject the life on Mars idea. But let's take a look at some evidence for autotrophism. Autotrophs are these bacteria that survive on not other life, but things in the environment. Those bacteria that oxidize iron ions in the water and make beds of iron oxide. Scott, what makes Mars red?
It's oxidized iron, right?
Iron oxide.
Now, how did that happen?
There are petatons of iron oxide. There's so much iron oxide on Mars that it looks red to the naked eye.
We can see it from here.
You can see it from here. And the question is, where the hell did all the oxygen come from?
Yeah.
In fact, the primitive Earth didn't have iron oxide because there was no free oxygen. Not in the water, not in the air. So where'd you get all the oxygen? If it's a geochemical process, tell me how you can have a geochemical process that floods the environment with enough oxygen to basically oxidize however many petatons of iron over the entire surface of the planet everywhere. It's ridiculous. There's no geological process that comes up with this much O2. None. There's none. And even if you took, it's crazy. If you took all the water on Mars and took all the oxygen out of it, it's not enough. It's not nearly enough to oxidize all the iron that's on the surface of Mars. We're not talking about the hematites and the special varieties. We're just talking about all the stupid iron oxygen. So you can see this from the naked eye, with the naked eye. And so spectroscopic studies, they found iron oxide. And of course, so did all the rovers. Iron oxide everywhere. That's what makes Mars the red planet. And oxygen itself, Scott, is such a reactive gas. Well, you know about the Apollo 1 accident, right?
Sure, it's horrible.
It's terrible. They pressurized the entire cabin with pure oxygen. Pure oxygen, if you're in a pure oxygen atmosphere, Scott, and you hold a big lighter to your hand will catch fire like a torch. Things that don't normally burn will burst into flame in a pure oxygen environment. And that entire capsule became a pyro bomb. It was a bomb. And the brave guys in it were fuel, along with all the wiring, all the sea coverings, all the foam, all the insulation. Everything that wasn't metal in there will burn in 100% oxygen. Oxygen is so reactive. Like I said, if we killed all the plants today, the year 2200, there is no oxygen in Earth's atmosphere or seas that's free dissolved oxygen. None at all, zero. It's all gone back into the crust in mineral form. So you get this crazy thing, and we start sending space missions, and Mariner 4 sends back the pictures. We've talked about that. They look more like the moon than the Earth. They took pictures of the Southern Highlands. They're finding all these craters. Looks very dry, it's very cold. They measure the surface temperature, of course, the Southern Highlands, the coldest place on Mars, minus 100 centigrade, 1% of Earth's atmosphere, no detectable water on the surface. Mars is dry, Mars is dead because there's no water. But every time they say you can't have life on Mars because some later experiment says, no, you're wrong, the conditions are suitable. We get Mariner 9, and I'll show everybody a single picture. And here's Mariner 9. And I think I can blow this up and move it over, and people can see it. And oh, look what we have right here. We have what looks like a dry waterway.
Yeah.
And when the dry Mars people looked at this, Scott, you know what they said? Oh, well, that's a rill like on the moon. It was a volcanic flow. There were people at NASA who said, no, 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 it's not a water course. That was liquid carbon dioxide flowing on the surface in a river.
Liquid carbon dioxide. Okay.
There are companies today that clean clothes with liquid CO2.
Yeah.
That is waterless. And so delicate fabrics and leathers, we clean with liquid CO2. You have to pressurize it to 4 atmospheres to get liquid CO2. Mars never had that kind of an atmosphere. Never. It's too small. Could never have a 4 atmosphere. Inconceivable. So you get the scientific community looking at every time there's evidence for autotrophic life, for autobiogenesis on Mars. It's kind of like the cardinal in Galileo's day, who was sent by, not by the Pope, but by the Inquisition to investigate Signore Galileo and his outrageous claims supporting Copernicus. And Galileo said, look, Your Excellency, here's my telescope. I've invented it. Look across the square there. Look how much closer it makes the buildings appear. Now let's point it at Jupiter. Look, and what do you see? There are moons orbiting Jupiter. Everything doesn't orbit the Earth. The cardinal looked, and there's various sources that give, I didn't put the name in that, the white paper I sent out, because various sources give different names for this guy. Cardinal Bellarmine, Cardinal Bernardo Gui. But in any case, he looks in the telescope and says, yes, I see it, but I don't believe it. Much the same was happening through the 60s and the 70s and the 80s and the 90s.
And the 2000s.
And the 2000s. People have said, I see it, but I don't believe it. And why not? Because we have a tradition now that's almost a century old that Mars is dry, Mars is lifeless, no water, no life. It's been a mantra in the scientific community for a century. Well,
A recent century.
a recent century. You get this interesting situation. You know, of course, why Einstein is famous. Because he was the first man in 3.5 centuries to make even a minor correction to Newton. Hawking is famous because he was the first guy in a long time to make a new rift on Einstein. And we find this stuff that's true. Why is Copernicus famous? He's the first guy in 2.5 millennia to make a serious challenge to Aristotle and Ptolemy with the geocentric model. This is very typical of science. Thomas Kuhn's Structure of Scientific Revolutions. Old theories don't die when they're overturned by new data. Old theories die when the last senior professor supporting them dies. This is why Chandrasekhar did not get his Nobel Prize for degenerate matter and white dwarf stars. Why? Because Eddington for 50 years said, don't give it to him, I don't believe it. We see this sort of thing in the history of science all the time. Next week, we're going to jump ahead to 1976 and the Viking landers. Viking had 4 experiments, and this was really, Carl Sagan had a big influence on this. Well, if you say there's no life on Mars, no life on Mars, no life on Mars, You're chanting it like a religious mantra. Let's go do a test and see. So they built Viking. There was a lot of public support. Why didn't you go look instead of just saying, I cannot? Go look. So we built Viking. Viking had 4 experiments. One of these was designed by a lovely gentleman, Dr. Gilbert Levin. And we're going to talk about Dr. Levin's results and the other Viking results. And we're going to see if we can't put another point on the graph. I tell people, quite honestly, I believe there is life on Mars. Can I prove it yet? No, I think that's going to take boots on the ground. But I want to show you, now I hope our audience has an interesting idea of autobiogenesis and how hard it is to sterilize a planet. You notice nobody who says, oh no, there's no life on Mars. Well, Steve Squires in 2007, right? Curiosity rover, Mars was warm, wet, and habitable, and it was an earthquake. NASA's official position is still no one has detected life on Mars. And in spite of what Steve Squires said, if Mars was warm, wet, and habitable, the history of the Theia impact says it's really unlikely that Mars didn't have life appear. And if it did appear, could simply drying out a planet and making it colder sterilize a planet? When I was a young man doing field biology, one of the things we did, we collect organisms, bacteria, mold, yeast. You know how we would preserve them, Scott? We would dry them out and freeze them. Process called lyophilizing. And we had stuff at the institute where I was working. We had samples of yeasts and mold and bacteria that were more than a century old that were still viable after being frozen. And we've seen, haven't we seen bacteria and viruses from 15, 25, 30,000 years frozen in the permafrost? And these things are viable. Haven't you seen posts online? These viruses could come out of the permafrost and kill us all. You know what? You can't kill things by freeze drying them. Certainly not biological, bacterial style life. Big animals, yeah, we die from freezing pretty easily. Little small unicellular life, not so much.
Pretty
Next
hard.
week, we're going to explore some more evidence from Dr. Levin's pyrolytic release experiment and gas exchange experiment and some others. And we're going to see what our audience thinks.
All right. Well, that's cool. We have, some of the other things that people might look into is Harold Urey and Stanley Miller's 1950s experiments.
Certainly.
Create that was the topic of the first video I just showed. We have some comments from our audience. Let's see. Cameron Gillis makes a point. He says, one thing I will say is life is rare and precious, an amazing thing no matter what your beliefs. Okay.
Indeed.
Let's see. Martin Eastburn made a comment about thermite earlier in our conversation. He said thermite welds railroad rails together.
Yep.
Massive heat and welded steel. Yeah, pretty amazing. I'll have to watch a video of thermite working.
Yes.
Wade Prunty comments, this is a great scientific discussion every kid should hear.
I put a couple of books up on the chat too, Scott. The Selfish Gene by Richard Dawkins.
Okay.
And Mars, the Living Planet, Barry D. Gregorio, and Gilbert Levin. That's Gilbert Levin's book, Mars, the Living
Okay,
Planet.
very cool.
He had a guy help him write it.
Yeah, Levin's kind of an unsung hero, I think, in all
He
of
is.
that. So
He is. If they ever decide to give a posthumous Nobel, Gilbert Levin will get one. But I think he's going to go down as, he's not the first certainly, but one of many great heroes of science who were not recognized in their own lifetime.
in their time. Cameron Gillis says, right on, Dr. Barth, but we must also consider the rate of change to slow evolution, to allow evolution to adapt. I think this is maybe in some conversation about the rate of how humans are polluting the earth. And
We
there's no
certainly,
doubt that we are doing that. But
there's no doubt, there's no question that a species can make the environment unlivable for themselves.
for themselves, this is the
But
real
the idea
subject.
that you can wipe out life on Earth or on a planet-wide scale is hubris. It's foolishness.
Yeah.
You can't do
And
that.
we psychologically think, well, if we're not on the scene, then there is no life, right? I mean, we're it, right? We're the only one that counts.
Hubris again.
We're the only one that counts.
Yeah,
Well,
when we
are
change
just
the
part of
environment,
whole,
we put environmental pressures and we accelerate evolution.
Yes.
But I stand by those principles that I
Right.
put earlier in. That doesn't mean that we shouldn't be good stewards of the
We
environment.
should be good stewards. We should be smart enough to be good stewards,
My question becomes, do we think we can control a planetary environment sufficiently well that we can continue to make it habitable and comfortable for us in perpetuity? I think that's probably hubris too.
Hmm.
You say, oh, global warming is occurring. Yes, the Earth has been warming for the past 25,000 years since the end of the last ice age. Then you say, oh, but are we contributing to the trend? Okay, but the trend was there before we were here. And, traditionally, the Earth in 4 billion years, the Earth's environment has never run away. Gone runaway inhabitable, never happened. Life tends to stabilize the environment in preference of itself, not in preference for a species, but for life in general. Consider the sun has gotten 25% hotter over the history of life on Earth. We get 25% more solar radiation. And yet the environment has remained very consistently stable because of a biology interacting with geochemistry to stabilize the environment.
To allow us to live. So that part's very interesting. Let's see. Harold Locke says, love today's lesson. Very new concepts I've never contemplated, but wow, they fit in my personal cosmological understanding.
I'm so pleased.
Let's see. And then Cameron Gillis comes back to say, the ingredients of life can reassemble, but it will be a different cake.
Quite so.
Sure.
Quite
Right?
so. Remember
Right?
the song MacArthur Park? I left my cake out in the rain and it's melting and I don't know how to make it anymore. Weird hit from the early 70s. Go look that up on YouTube, MacArthur Park.
I'll have to look it up.
Yeah, it's crazy. You'll love that. Sounds like the guy who wrote it was on acid at the time, but it has some relevance to our conversation
Right.
today.
That's right. Let's see. Martin Eastburn says, I worked in Silicon Valley. A LOX truck turned over and was pouring liquid oxygen, I guess, across the blacktop. Cars were causing detonation with tire pressure. Police
Yes.
walking over it. Police warned walking over it or through it.
Oh, I wish I had, it's a terrible, tragic accident happened, but the physicist in me and the chemist in me
How
says,
cool, huh?
I want to see, I
Right.
want to pour liquid oxygen across the blacktop and send an RC car across it and see if I can make it go bang.
Yes. Cameron Gillis says, excellent deep session, Dr. Barth. And let's see. Billy Beckett says, another, how do you know, has left me much more enlightened.
Well, I appreciate that. That's very kind of you. Thank you.
And Cameron just puts in, as we learned about how to live in space with artificial environments, I believe this will help us better manage our Earth's atmosphere.
I
Very
hope so.
possible, the
I hope
things
so.
that we learn act as a mirror, as to how we should.
Although
probably live.
the autobiogenesis of life tends to prejudice an environment for life, and it tends to adjust the environment to be favorable for life. And we see nothing in the history of life on Earth that indicates that the environment gets adjusted for a particular species. Life in general, yes. Individual species, no. They come, they go. The case for Mars and why we must go.
That's part of the adaptation of life anyways, that,
Yes.
right?
Yes.
That it could morph and change and fit and thrive. So, so if you've been staying up late at night worrying about how we're destroying the planet, you can rest easy. The planet's going to be just fine.
The planet's going to be just fine. We
Just
may
fine.
not.
Yeah,
But,
we
yeah,
may have to adjust our living style, or we're here to learn and observe and be part of this giant parade of life and all of its diversity.
Indeed. And I am as human-centric as anyone. I want our species to survive.
Sure.
The dinosaurs had a almost 250 million year run, 250, 300 million years. But I don't know. And some species, turtles and alligators, have been on the planet for a long, long, long time. Certain bacteria, we have archaeobacteria that have been on the Earth for billions of years. But in general, species come, especially the more complex we get. Species come, species go. The simpler life forms tend to last much longer because their requirements are much less stringent, much more broad. But I put a couple of books in the chat for everybody, Scott. The Selfish Gene by Richard Dawkins, Mars, the Living Planet by Gilbert Levin, and The Case for Mars and Why We Must Go by Robert Zubrin. And I'm hoping maybe some of our folks will come, and I'll try to get the next week's show written and up quickly. I'm getting ready to launch back into school. My classes start next Monday. So the fuse is getting very short before I get very busy again. And but I'm going to make a commitment.
That means you'll physically be back in the classroom, correct?
Correct. And hooray for that. For a while anyway. My crystal ball is broken, but yes, we're going back to school next week physically, which I'm looking forward to. And I'm going to make a commitment to do my very best to continue to do weekly shows with everybody here. If we miss a week around finals time, I hope you all forgive me.
Yeah.
But basically,
you got to put food on the table first, and you have a responsibility as a.
I do, and my students, God bless them, pay vast sums of money to come and sit in the classroom with me and listen to me prattle on about this, that, and the other thing. But I am teaching a section of astronomy for educators.
Awesome.
I'm working on the new book, Star Mentor. My students are going to whine about, you're making us write 3 pages a week, but I've cranked out 85,000 words, 325 pages in the last 4. I'm starting on my 5th week. So in 4 weeks, I've done 85,000 words. So I'm not going to, when I say I need a couple 500-word essays a week, I'm not going to be sympathetic about the whining.
Right.
But the book is going well, and I hope the audience here will be some of the first. I will let you know when it goes in for
amazing
the production process.
We look forward to it. Okay, so tomorrow we will have our regular Tuesday programming, but it's going to happen an hour earlier. So the Open Go-To Community Live will start at 3 p.m. Central. And the reason why I'm doing that is we have I have to be in a Zoom meeting to prepare for the Starmus or Starmuse, I think it's pronounced Starmus actually, event that's going to happen next year in September. And that's going to be in Yerevan, Armenia. And so Explore Scientific, provided that the pandemic is receding, or we have turned the corner more. We will be flying to Armenia to host a free star party for thousands of people in Yerevan, and the Starmus event has people like Brian May and Peter Gabriel, and so it's a combination of music, physics, astronomy, and so it's going to be a really amazing event. I've heard about it for years. Stephen Hawking was one of the founders of this event. David Eicher is one of the people that's on the board. Garrick Azraelian is credited as, I guess, the main guy who started the whole event. So I love it. I love the concept. We want to be there. But we have to do a little bit of planning to get the ball rolling. So, and our schedules had to all be adjusted so that we can do this. But thank everyone that watched today and came back to see our programming after we were gone for a week. There's always the worry that you'll come back and you'll just hear crickets on the other side, but Now, crickets may be the other animal that lives for a very long time after we're gone. I don't know. But anyhow, it was very enjoyable, Dr. Barth, and I learned a lot today too. And that feeling of kind of an enlightened feeling, or at least reframing how you think about life and what it means to you, psychologically, spiritually, whatever, these kind of things hit to our core. And I think it's healthy to examine that and question that and try to, flip over the rocks and see what's underneath there. So that's what you do every week for us, Dr. Barr. So thank you very much. And we will see you guys tomorrow. Tomorrow we also have Global Star Party, our 58th event. The theme is moons and moonlets, and we have a great lineup for you. One of the people that will be rejoining us after being gone for a while is John Briggs. We will have Sabella will be back on, people that are normally on our program, including, of course, Dr. David Levy. Dave Eicher will be on. So it should be a great show. I'm not getting everybody, but it'll be a lot of fun. And we welcome you to start tuning in at 7 p.m. Central for that tomorrow. And if any of you would like to join Global Star Party, get in touch with me directly or in touch with us directly by emailing explorealliance@explorescientific.com, and we'll make arrangements. Okay, so you guys have a great evening and take care.
Bye, everybody.
Bye.
We all want to know where we came from. Everybody asks that question. And also, could life exist elsewhere?
A little piece of the puzzle is actually, if you want to look for life on other icy worlds other than Earth, then you have to understand life on Earth first. It beautifully simulates how a hydrothermal system under the right pressure and temperatures would flow continually.
Everything requires energy input, especially when you're talking about organic synthesis. The great thing about these hydrothermal vents is you have a lot of free energy already there. You really can start to link up these organic molecules and form longer chains, and those longer chains are really the key to getting to DNA synthesis. It's all worth it to really show how you can test these reactions almost to the same scale that you have on the bottom of the ocean. It's very rewarding to see it really come about and come to fruition. We're starting to just explore these icy moons and icy worlds where you could possibly be reproducing the same things that we find on Earth today with these rock-water interactions. So it's important for understanding how do we search for life on other planets, and also how did life actually begin here on Earth.